we're getting down to the nitty-gritty now. We're going to be able to start solving for solutions to differential equations. All right, what I'm going to do is I'm going to prove to you, I'm going to solve that dp over dt equals ky, okay? Or I'm sorry, kp. And I'm gonna solve this and prove that the solution to this is p of t equals p naught e to the kt. Now, a couple things to remember. First things first is that k represents the relative growth rate, right? That this differential equation can be spoken as the rate of change of the population with respect to time is proportional to the amount of the population present at the time, okay? And I'm going to go from here to here and I'm going to show you. Now, one piece of information that we need is to be able to solve this differential equation fully, we need to show, or we need to know that when we know that p of 0 is equal to p naught, which implies we have the initial value of 0 comma p naught, right? We agree with that. All right, now watch how I do this, because it's basically the same every single time, but I'm going to do a few of these with you to get you up to speed. The cool thing about writing a differential equation in this way is that it's in Leibniz notation. We've done this a bunch. We did it in integrals. In Leibniz notation, this is separable. So what I can do is I can rewrite this as dp over p is equal to k dt, right? That's all it is. dp over p is equal to k dt. I just split it up algebraically. Now you may say, wait, Ripley, that's kind of cool. They both have a dp. They both have this differential. Oh, that's why differential equation. Huh. Anyway, remember, it's still an algebraic thing. I can do whatever I want to both sides as long as I do the same thing and I'm not dividing by 0. So guess what I'm going to do? Whoop. I'm going to take the integral of both sides. Why did I choose to do that? Well, because I saw the d's and it looked kind of interesting. It looked fun. So here I go. I'm off to the races. I know if I take the integral of both sides, I'm going to get the natural log of the absolute value of p is equal to kt. Now you may be going, Ripley, what about the plus c's? Well, I'm going to address that. I'm going to keep it simple. Rather than plus c here, and put a little plus c here, and then a plus c here, they'd have to be different theoretically, and then I would subtract this over, and guess what? I would get a plus c, because it's going to be some constant, assuming that they're different, right? So I'm just going to put it on one side. That makes everybody happy, all right? Now, this absolute value is going to give you guys some fits, but don't panic. I want to show you something. What I'm going to get is, remember, at the end of the day, I'm trying to solve for p because the solution to this differential equation is p of t. I'm going to solve for p. I want p all by itself. So I know the absolute value of p is going to equal e to the kt plus c. Okay? Now, that implies that p, right? I just took e to the both sides. Sorry, I probably should have showed you that. Whoop, whoop. And this gives me this, kt plus c. That implies that p, to strip off the absolute values, p is going to equal plus or minus e to the kt times e to the c. Do you agree with that? Now I'm going to do something here, and it may drive you a little bit crazy, but don't let it drive you crazy. It doesn't matter if we use the plus or the minus, because what I'm going to do is I'm going to rewrite e to the c as just a new arbitrary constant. This is e to the kt times, we could send this plus or minus over here, but I'm simply going to write it as a. Now I don't have to include the plus and minus in that, because that plus and minus will be taken care of when we use the initial value. It will be determined whether a is positive or negative with the initial value. So this becomes a e to the kt. Now that may look like voodoo, but if you think about it for a second, this can either be plus or minus depending on the value of p at time t, right? Which, if it depends on the value of p at time t, then that implies that we're using the initial point, whatever the initial value is. So I have p equals a e to the kt. Now I need to solve for a. Well, I have an initial value. So I know this implies that p of 0 is equal to a e to the k times 0. Well, k times 0 is 0. E to the 0 is 1, so this implies that A equals P of 0, which we affectionately call P naught. Hey, guess what? We just did it. We know that a big implication here is that P of T is equal to P naught, because that's what A was, E to the KT. And we're done. QED. QED is Latin for I win. Sorry. All right, now let me do another one for you, because these can get a little hoopty, and there's some rules here, okay? I'm going to take the differential equation dy over dx. I'm going to solve for the solutions, and I've got, let's see, what do we got here? I got x squared over y squared, okay? And I'm going to assume that it passes through the point 0, 2. Because remember, if I don't have an initial value, if I didn't have an initial value here, I would be done at this step. This is the family of curves, and we know what this family of curves looks like. They're exponential growth and decay problems, true? Excuse me. However, to find a unique solution, then I need a point to pass through. So I'm going to use 0, 2 just because it looks like fun. All right, so same trick, dy times y squared, just using algebra, is equal to x squared dx. Got them separated. At this point, notice the y's are with the dy and the x's are with the dx, so I take an antiderivative. This gives me y cubed thirds is equal to x cubed thirds plus c. Okay? I'm going to multiply through by 3, and I should get y cubed is equal to x cubed plus, now, if I multiply c times 3, I'm still just going to get another c. And that c will be taken care of with my initial value. Okay? Now, there's a trick here. And you don't have to do this. You just make your life easier if you do. I need to, at this point, solve for c. Now, you may be saying, but Ripley, why don't I take the cube root of everything? Well, I can. I totally can. In fact, I will, just to show you guys. If I take the cube root of everything, what I end up with is y equals the cube root of x cubed plus c prime, right? It's there. However, oh, and please, in the name of all that's good and holy, a mathematician weeps every time that a student takes the cube root of a sum as the sum of the cube roots and rewrites this as x plus something. Remember, any root of a sum is just the root of the sum. You're stuck. Now notice though here, to use my initial value and to solve for c prime, then I have to cube everything again. So, and you'll get a feeling for when to do this. This is the best step to solve for c prime, isn't it? Because I know that y cubed, well, y is 2, so then I know that 8 is equal to 0 cubed plus c prime, so c prime is just equal to 8. It's a lot easier to solve algebraically. The only reason I solve for it here is because it makes my life simpler, and that's all that I'm trying to do. So I know that y is equal to the cube root of, I just solve for c prime, so this becomes x cubed plus 8. I'm done. There's nothing to it, right? That's easy. All right, there's one other one that I really want to show you. This is kind of a biggie, because it's got some really important rules in it. Oh my goodness. This notebook only has 100 pages in it. Whatever will I do? I still have two videos to do. Looks like I'm going to have to meet you guys in another notebook here in just a sec. I'll see you in a second. Bye-bye. Wow, that was crazy. I had to make a new notebook. Kind of feel good, though. That was killer. Okay, so let me do one more for you, because this one's really important. And it's got some tricks in it that'll make your life easier. And if you, I'm going to give you advice, and if you choose not to heed that advice, you're going to suffer at your own hands, potentially. All right, I'm going to say that dy over dt is equal to 15 minus 3y. Okay, now there's a rule that I always tell my students. And let's say that this passes through the point of, I don't know, I'm going to keep it super simple. I'm going to be lazy. F of 0 equals 0. All right, so I've got this initial point, 0, 0. But way more importantly than the initial point, because I could have picked any two values, is this trick. The rule is this: do not separate your variables Okay, do not separate your variables until you have the coefficient of the y value equal to 1. You may be going, really, what are you talking about? I can't make it equal to 1. It's going to make my life harder. And that is a little bit nebulous what I'm saying. What I'm saying is this. Notice that there is a -3 in front of the y. And if you've heard me say it once, you've heard me say it 1,000 times. Respect thy negative. So I can rewrite this as -3 times y minus 5. So what I mean by I want my coefficient of the y term, in this case the dependent term, I want it to be 1. In other words, I'm going to leave behind any constants that were there in the first place. So had this been a +2, I would factor the 2 out. In this case, it was a -3, so I get rid of it. Now, the reason that I do that is because if I don't, I open myself up to some crazy opportunities to make stupid mistakes. Now, I'll do it. I'll do this problem without factoring out the -3 first, but I want to show you how hoopty it can be. Now that I have the coefficient inside the parentheses of y as a +1, I separate. So I get dy over y minus 5 is equal to -3 dt. Now, that negative can make you nuts. That's why I got rid of it. So and now it's all by itself over here. We are happy. We're just as pleased as we can possibly be because now this is a super simple antiderivative to take. Had I left the -3 here, now I have to do a u substitution, or I got to remember that Ripley trick with when I'm composing with linear terms. All right, so I got this and I got this. This becomes the natural log of the absolute value of y minus 5 is equal to -3t plus c. Now, I take e to the, and I'm not going to go through the whole absolute value thing with the, remember what I did at 100. I'm not going to go there. I got to change notebooks. But I can simply say if I take e to the both sides, I get y minus 5 is equal to a e to the -3t. That a gobbles up the plus and minus that we have to deal with the absolute values. So y of t is equal to a e to the -3t plus 5. Then I can stuff in 0, 0. So I know y 0 equals a plus 5. So a equals -5, which would imply that y is equal to 5 minus 5e to the -3t. And I'm done. Nothing to it. It's easy. It's super easy. Now, if I don't do that, watch what can happen. Let's say, let's go over here. Let's say that I disregard Ripley's sage advice, and then I get dy over 15 minus 3y is equal to dt. Take the antiderivative. Now, this is fraught with peril. That's supposed to be a 15. I don't know what the heck that was. This is fraught with peril because you may forget a couple things. You may forget that negative, and you may forget that coefficient. The most common error that students make is they just say, oh, this is easy. I got the natural log of 15 minus 3y, and then they're done, equals t plus c. Well, that's not true because if I take the antiderivative of this is a linear term, this would have to be over -3, wouldn't it? So now I have the natural log of the absolute value of 15 minus 3y. You see how when I go away. I know I'm brilliant. Not really. Notice when I factored it out first, it made all my terms just nicer. They're smaller. They're easier to work with. So what do I got here? I have, what the heck do I have? I've got equals -3t plus c prime because it's a new c. I have 15 minus 3y is equal to a e to the -3t. I have -3y is equal to a e to the -3t minus 15. And now I have y is equal to, if I divide through by -3, I get a +5 plus a prime, because now I've got a new constant, right? A divided by a constant is just another constant, e to the -3t. Look at how much more work this is. Now, I still got the same initial value, so 0 equals 5 plus a prime times 1, because e to the negative, you know what I'm saying. E to the -0 is 1. So when I solve, I still get a prime equals -5, which implies that y of t is equal to 5 minus 5e to the -3t. But look at how much more work it is. every algebraic step you take increases the likelihood that you're going to make an algebraic error. So do the heavy lifting in the beginning to make that coefficient of your dependent variable 1, and then life is good. Okay, that's it. Thanks for listening. I hope this was helpful. You're going to do a bunch of these. Guaranteed, if you're taking the AP exam, if you're taking this course to take an AP exam, you are guaranteed to have a free response problem show up where you have to solve for a solution of a differential equation using using separation of variables, and it's always worth a lot of points. So if you are taking this as an AP course, make sure that you spend a lot of time practicing with separable differential equations. All right, enough yapping from me. I'll talk to you guys later. Have a good day.